Hello everyone, we are at Team MEO2, the development of a field agri-robot for crop health monitoring. Our team members are Ryan Murphy, Mihir Nene, and Alicia Jackson, and our faculty advisor is Professor Chengyu Cao. Our project sponsor was AgriVolution. The farming population in the U.S. is gradually aging and dwindling, but the demand for food is ever increasing. There is an increasing need for locally, sustainably grown food, as exemplified by the current supply chain disruptions due to the coronavirus pandemic. Our project is to fill a market niche by developing an agricultural robot prototype that can be deployed in a field to monitor crop health. The prototype will do so by moving autonomously through crop rows and stopping intermittently to take and process pictures of crops to determine their general health. This data, along with the corresponding GPS coordinates, temperature, humidity readings, will be sent back to the farmers to assist in their attention to application of pesticides or fertilizer to concentrated areas instead of mass spreading them across the entire farm. The specifications of the prototype requirements were determined by a balance of robot weight, motor torque, and battery capacity. Setting these specifications was an iterative process, revisited multiple times because these requirements are dependent on one another. Increasing the distance that a robot will travel in one day causes an increase in the required motor torque and speed, and this causes each motor to use more power, which increases battery capacity, and so on. We used an iterative spreadsheet to determine the appropriate specifications of daily distance goal, average moving speed, robot mass, required motor torque, and required battery capacity. The motor torque is shown to be a function of wheel radius, robot mass, required acceleration, surface incline, and surface coefficient of friction. Our specifications required large values of total torque for our operation, up to 5.25 Newton meters, so we decided on an all-wheel drivetrain to spread the torque between four motors. The total required battery capacity is a function of the motor torque and angular speed multiplied by 4 to account for each motor. We selected motors that fit our requirements for torque, RPM, and operating current, and were at a relatively inexpensive price. Price was important here due to this prototype needing to be accessible to small farmers. Then we decided to fabricate our own battery from a collection of small lithium-ion battery cells. These are connected with the safety battery management system. This battery was chosen to meet our exact power requirements at a light weight and at a much less expensive cost than a pre-made solution. Our battery consists of 24 cells. With a combination of series and parallel connections, the total battery operates at 12 volts with a 20.7 amp hour capacity. We studied 5 main materials for the robot framework, including aluminum, steel, plastic, wood, and acrylic. Each material was evaluated for the major categories as shown in the chart. Aluminum was chosen from these materials mainly due to its strength-to-weight ratio, machinability, scalability, corrosion resistance, and thermal conductivity. Our prototype design incorporates 2 raised legs to lift the robot base off the ground in order to avoid damage from small rocks on the surface. This allows the robot to travel over ground objects while continuing to move. Our final prototype is completed with an ABS plastic exterior casing to weatherproof the components for outdoor operation. Plastic was chosen due to its strong weatherproofing ability and its light weight. Each of the 4 motors are connected to the wheel shaft at a 90-degree angle with a 1-to-1 bevel gear system. This allows for the motors to be raised further off the ground and protected from collisions with small objects. The wheels are still able to rotate with the same intended torque ratio due to the 1-to-1 gear ratio. There is minimal loss with these gears. Each of the legs is on a separate rotational axis from one another, allowing one leg to lift up while the other stays flat on the ground. This design was incorporated so that the robot can traverse over small rocks in the soil while continuing its motion. Our prototype relies on a number of programmable components to perform its autonomous operation. The robot uses 2 cameras on either side of the prototype to detect diseases in crop leaves. This process is accomplished with machine learning artificial intelligence software. The robot has an onboard transceiver to send images of diseased crops back to the farmer with a GPS tagged location. The robot is able to autonomously navigate through a pre-programmed path with a GPS module and uses 5 ultrasonic sensors working together for object avoidance. Here is a demonstration of the prototype operating autonomously on a pre-programmed path. The robot is seen accelerating, braking, and turning. The GPS antenna allows the robot to operate on a pre-designed path, as can be seen by the robot's ability to make it to the red flags. Despite the difficulties caused by the current coronavirus pandemic, our team managed to adapt our design and complete the robot prototype. Unfortunately, the delays left us unable to complete the testing we had planned. We plan to test the key features of the robot, including its range, battery life, acceleration, and ability to overcome inclines and uneven ground. Additional tests would have been conducted for its weather resistance. Based on the results of this, we would reconfigure the design as necessary.